So today we're going to start Unit 5, Lecture 1, where we're going to be discussing lipid structure. So just as we have different classes of carbohydrates, we also have different classes of lipids. These classes consist of fatty acids. We have complex lipids, which includes our triglycerides, triacylglycerides, abbreviated as TAG all throughout this lecture. We have phospholipids and glycolipids. We discussed glycolipids a little bit in the carbohydrate lectures. So glycolipids are lipids that are conjugated to a carbohydrate. And then we have these derived compounds, which are biochemical compounds that are synthesized from lipids, including sterols and leukotrienes. So our sterols include cholesterol, leukotrienes, and prostaglandins. Those are signaling molecules, and we will talk about those in a few minutes. So first we're going to focus on fatty acids and the chemistry of fatty acids and what makes them and the characteristics of fatty acids. So here we have our basic fatty acid structure. You could see that we have a methyl group on the end with our carbon and our 3 hydrogens. So carbon and 3 hydrogens is a methyl group. This is also referred to as the omega end. And on the other end, we have our carboxyl group, which is a COOH, so we have a carbon double bonded to an oxygen and a hydroxyl group. So this is the water-soluble end, and this is also referred to as the delta end. So when we are discussing the different types of fatty acids and classify them as omega-3 and omega-6, that's starting from counting at this carbon. Traditionally, we normally in organic chemistry start at the carboxyl end, but with the omegas, we're starting at the hydroxyl or the methyl end. And then what is making up our different fatty acids is the length of the carbon chain. So we have our carbons with our hydrogens here. And this is basically what's making up the characteristics of that particular fatty acid. So they have a methyl end, they have a carboxyl end, and that chain in the middle is what is determining the characteristic of that particular fatty acid. So when we have straight carbon chains and no double bonds, that's what we refer to as our saturated fatty acid. So here we have stearic acid, which is 18 carbons long, and you do not need to know the name of stearic acid or that it has 18 carbon, that it's 18 carbons long. Just basically, it's an example of one of the saturated fatty acids that are synthesized and found in our diet. So it's a very simple structure. You can see there are no double bonds. We have our methyl end over here, our carboxyl end over here, and a bunch of carbon chains in the middle. And if we remove some of these carbons, we're going to have a different fatty acid. So if we have 16, it's palmitic acid. And if we have only 2, just the methyl end and the carboxyl group, that's acetic acid. Our next category is our monounsaturated. So what does unsaturated mean? Unsaturated means that there is a double bond. So here we can see our oleic acid, which is 18 carbons long, and we have this double bond at the 9th carbon. So here, starting at the methyl end, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. That's where that double bond is. So it's right in the middle. Oleic acid is most commonly found in our olive oil. It's a pretty healthy fatty acid that you can consume. So once again, mono meaning 1, unsaturated is this double bond. So we have monounsaturated, and our main example of that is oleic acid found in olive oil. And then our last classification is our polyunsaturated fatty acids, which are also referred to as PUFAs. The two most common polyunsaturated fatty acids are linoleic acid and linolenic acid. And the poly, you could see here, means greater than one double bond. So you can see that linoleic acid has two double bonds. We have 1, 2, counting from the omega end. And our linolenic acid has 1, 2, 3 double bonds starting from the omega end. So 1, 2, 3 carbons, 6 carbons, 9 carbons. And this is also what's making up the omega-6 and omega-3. These are the two most common omega-3 and omega-6 fatty acids that you're going to encounter. And you could see with the amount of unsaturated bonds, why our polyunsaturated fatty acids are so susceptible to oxidation. So that's what's going to cause rancidity within these fatty acids. So these are the least stable. So the greater the amount of unsaturated bonds, so greater double bonds, the less stable. So this is why you need antioxidants within your diet, is so we can maintain these double bonds. So if we have antioxidants, vitamin E, ethoxyquin, etc., that they can maintain and help keep these double bonds intact so they are less susceptible to oxidation and degradation. All right, so now we're going to talk about how the structure affects the characteristics. So here on the right-hand side, I have many of the structures of the various fatty acids that we're going to be discussing. So here we have our omega-3 polyunsaturated, which is EPA, DHA, and alpha-linolenic acid. Then we have our omega-6, which is arachidonic acid and linoleic acid. Our monounsaturated, our oleic, and two of our most common saturated fatty acids, stearic and palmitic. So the greater the unsaturation, the lower the melting point. So this means that they're going to be liquid at low temperatures. So this is why if you could put vegetable oil in your refrigerator and it's not going to get solid. If you put it in your freezer, it'll get solid, but it'll stay as a liquid at refrigerated temperatures. And the opposite is true. So the greater the saturation, the higher the melting point. So if we were going to classify these, our omega-3s are going to be more liquid at colder temperatures. So these are the most liquid. Our omega-6 are going to be, they're also going to be more liquid, but they will be less so than the omega-3s. Our monounsaturated fatty acids or oleic acid is going to have a higher melting point than our omega-3 and omega-6. So currently there is, I recently read a report that a lot of olive oil companies, for instance, since olive oil is worth a lot of money, it's more expensive than regular vegetable oil, there's a lot of fake olive oil on the market. So a lot of these companies are putting regular vegetable oil from corn and soybeans into the bottle that says that it is olive oil or extra virgin olive oil, and it's just not the case. So one simple test that you could do to see if your olive oil is legitimately primarily oleic acid is stick it in your refrigerator. So your monounsaturated fatty acids, your oleic acid, is going to become solid at a refrigerated temperature. It's still liquid at room temperature, but it will become solid at a refrigerated temperature. If it is still liquid, then you've been duped and you have paid extra money for a lot of vegetable oil. And then our saturated fats, these have the highest melting point, so they are basically what's making up our butter. So this is the reason why our butter is still solid at room temperature. In addition, we have these other fatty acids that we haven't talked about. So we do have some odd-chained fatty acids. These and our branched-chain fatty acids. So both our odd-chain fatty acids and our branched-chain fatty acids have lower melting points. So they will be more liquid at lower temperatures. So our odd-chain and branched-chain fatty acids are primarily coming from bacteria or various other microbes. Most mammals are not able to synthesize odd-chain and branched-chain fatty acids. There are some species, for instance, lamb has one of the reasons why it has its very specific odor and taste is because lamb has a lot of branched-chain fatty acids, and that's mainly not because the lamb is making it, but the microbes within the rumen are making these branched-chain fatty acids. And that's what's giving them their distinct flavor and taste. It's also why, if you know some cultures, people from the Middle East or Mediterranean area, so including Greek and Italian and Middle Eastern countries, they will say that lamb from their countries has less of that American lamb taste, and that's basically because of what they've been fed. So lamb in the U.S. has more grain-fed, which results in more branched-chain fatty acids. And then we also have our short-chain fatty acids, also referred to as our volatile fatty acids. So you should be able to tell me what these are. So this would be our acetate, butyrate, propionate are the big three. So they have a low boiling point. Boiling point means that they are going to be a gas at a lower temperature. So they are very volatile in their free form. So volatile meaning unstable. So how can you determine the degree of saturation without, if you're a company, if you're a feed mill and you want to make sure that the fat that you're getting is what you paid for, there is a test where we look at iodine number. So you can see here with our linoleic acid, we have 2 double bonds. So if we add in a known amount of iodine, the iodine is going to react with the oleic acid. So where there are double bonds, we're going to break those double bonds and add our iodine. And then we are able to put that on a spectrophotometer and read the absorbance of the color. So iodine, if you remember, has a very dark brown color. So if there is, and for all intensive purposes, our fats are colorless. So if we have a lot of linoleic acid, which is colorless, we add in brown iodine, that iodine mixes, this also ends up being colorless. Now, if we have stearic acid, which is our saturated fat, then this iodine is going to stay brown and our fat is not going to interact with it. So therefore, we end up having that our saturated fat has a value of 0 for the iodine number. And then the greater the amount of unsaturated bonds that it has, the greater the iodine number. So our linolenic acid is going to have a higher number. I believe the iodine number is around 170. Now, there is a process, if you've taken any food science, you may have learned about hydrogenation. So hydrogenation is where we actually are taking an unsaturated fat and making it saturated. So this goes unsaturated, goes to a saturated fat. So why would we do this? Well, especially in the food industry, the margarine industry, back in the 80s when it was discovered that saturated fat was bad, they needed to come up with an alternative. So it was shown in the 80s that the greater the saturated fat in your diet, the more at risk you are for atherosclerosis. So therefore, they decided, they being the food science industry, that they would hydrogenate the unsaturated fat and basically make margarine. So that's what margarine is, where you use vegetable oil and you add hydrogens, and basically we're making a saturated fat. So we're removing the double bond, adding hydrogens over here. And the benefit to that was now you had quote-unquote spreadable butter that did not have to be left out on the counter all day in order to utilize or be melted on the stove or in a microwave. And that was great, and not all of the fat ends up becoming hydrogenated. So overall, it ends up increasing the amount of unsaturated fats that you're consuming within your diet. The downfall to this process is where we get the going from our cis. So up here we have a cis bond where the hydrogen's on the same plane, to where we have a trans configuration. So you could see our hydrogens are on opposite planes. And we'll talk about this in more detail in a few minutes. So our hydrogenation, we're able to reduce the amount of hydrogens from our carbon double bond, and if we have complete hydrogenation, we get a saturated fat. The side effect is the formation of the trans fats. So then this ended up leading to a lot of companies. So trans fats actually ended up showing that they are just as bad as saturated fats, if not a little worse, because not only do they increase the amount of LDLs, they decrease the amount of HDLs, which are pulling cholesterol from your cells to be cleared by your body. So we have less HDLs, more LDLs, where saturated fat just resulted in higher LDLs. So that resulted in many of the companies. So now you will see a lot of the marketing that will say 0 grams of trans fats. So if you're reading your "I can't believe it's not butter," etc., you will see on your container it'll say 0 grams of trans fats, because they're saying that they actually verified that all of their hydrogenation is complete. Okay, getting back to our isomers. So as with our carbohydrates and our amino acids, our fatty acids also have isomers, where in carbohydrates and amino acids, we refer to them as D and L. Here, with our fatty acids, we're referring to them as cis and trans. So here we have our saturated fat, our stearic acid, which is what's found in butter, and then we have our linoleic acid, which is found in vegetable oil, and here we have this cis double bond, and you could see our hydrogens are on the same plane. If we have incomplete hydrogenation, we're going to have our hydrogens are on opposite planes. So this is a trans fat. So cis is the same, trans is opposite. And our trans fats have a higher melting point. So they are more similar to our saturated fats. So it makes sense, because if you look at the kinkiness of our fatty acids, our saturated fats are not kinky at all. They are straight as an arrow, which is easily stackable, etc. And then we have our standard unsaturated fats, and you can see how kinky it is, especially if you add linolenic acid, which has even one more additional double bond, so it makes it very, very kinky. When we add or have the trans form, you can see it's more similar to our saturated bond, and that's why, so our trans fats are also going to be more solid than our oils or our cis. So we do have some essential fatty acids. So just as we have essential amino acids, we have essential fatty acids, and it's because of this why you need to have some fat within your diet. So these are essential because they cannot be synthesized in vivo, which means in your body. Your body cannot synthesize them. But we need them for proper membrane synthesis and function. We also need them for synthesis of these signaling molecules referred to as prostaglandins and leukotrienes. Now, mammals can make double bonded fatty acids. However, we are not able to we do not have the enzymes able to synthesize at the omega-3 and 6 end. So we can do omega-9, 12, but we cannot do omega-3 and omega-6. So therefore, they must be obtained from plant or marine life. So many of us have heard of omega-3 and omega-6 fatty acids, and you may have heard that your omega-3 fatty acids are more healthy than omega-6. So what are these and what is the function? Why are they so essential? So our linoleic acid, when we consume that, so this is our omega-6 starting here, we utilize this to make arachidonic acid. So this makes arachidonic acid conditionally essential. So some animals, it is essential. So we use linoleic acid, we elongate it and desaturate it, and we get arachidonic acid, which is 20 carbons long and has 4 double bonds within it. Our next is our linolenic acid. So our linolenic acid is our omega-3 over here. So it is 18 carbons long, 3 double bonds, and it is what is used to make eicopentanoic acid, or EPA. And then our EPA here, which is 20 carbons long and has 5 double bonds, is then used to make DHA, or docosahexaenoic acid, DHA, which is 22 carbons long and has 6 double bonds. So you've probably heard of EPA and DHA. So our arachidonic acid makes, and our linoleic acid, they are pro-inflammatory. So these prostaglandins and leukotrienes that they are synthesizing are pro-inflammatory. So basically, anytime you have any damage done to your cell, you're going to be triggering the breakdown of your fatty acids, and those are signaling your immune cells that we've been damaged, there's a potential breach, we may have a bacterial or viral infection, come help us. So those are, some of those signaling molecules are prostaglandins and leukotrienes. So we break down those fatty acids that make up the phospholipid to signal the immune cells. Our linolenic acid and our EPA and DHA, these are anti-inflammatory. So they actually reduce the amount of inflammation. So because of this, this is why our omega-3 are viewed as better for you, or reduce the risk of atherosclerosis, because a lot of the problem with atherosclerosis or plaque buildup in your heart is that it's a macrophage, part of the immune cells, that are actually sending too many signals saying that there's an infection when there is not. So if we have more of our omega-3s, we're going to reduce that amount of inflammation. Now, our linolenic and our linoleic acid, they compete for this delta-6 desaturase. So this delta-6 desaturase, delta is going from the carboxyl end. And so they're competing. So it all depends. If you have a significant amount of omega-6, you're going to be more likely to make arachidonic acid because you're going to have more omega-6 that's able to take up the delta-6 desaturase. In addition, our linoleic, our omega-6, has a greater affinity for the delta-6 desaturase. And then we have our arachidonic acid and our EPA compete for our delta-5 desaturase. So therefore, these two are competing. And one of the reasons why we have a reduction in the amount of EPA or conversion from EPA to DHA is because of this competition with the delta-5 desaturase. So this is basically the same thing as the previous slide, just another way to show it. So here we have our linoleic acid, we have our delta-6 desaturase, and our linolenic acid, our delta-6 desaturase. And you can see we're having our EPA, forming our EPA here, or arachidonic acid. When these two are broken down from the phospholipids, you can see they use the same enzyme. So if we're making our prostaglandins, we're using cyclooxygenase, or COX. If we are making leukotrienes, we're using lipoxygenase, or LOX. And these are competing for these two enzymes, so they use the same ones. So when we have arachidonic acid broken down to prostaglandin PGE2, that's pro-inflammatory, or if it's broken down to LTB4, that's pro-inflammatory. When we break down our EPA and DHA, we're going to get PGE3, which is anti-inflammatory, or LTB5, anti-inflammatory. We have here our omega-6. As I mentioned before, our arachidonic acid, which is abbreviated as AA, it is conditionally essential. Same with EPA and DHA. These are also conditionally essential, but they are essential for the cat. So the cat does not have these enzymes. It does not have the delta-6 desaturase, because they are obligate carnivores. They should have adequate amounts within the diets that the animals that they're consuming. So here's basically the same thing again, just written in a different way. So those of you that like more bullet points or whatnot, this is the slide for you. So here we're having our linoleic is converted to gamma linoleic acid, and then it converts that into arachidonic acid. So we can put arrows in here. And these are pro-inflammatory. And then you have omega-3 alpha linolenic acid. And this is found in your green leafy vegetables, flax, flaxseed, canola, walnuts. And it is converted to EPA. Now, this conversion rate is really low. It's only about 1% in males and 3% in females. And this ranges greatly depending on the individual, and we'll talk about that in a little bit. And then we have going from our EPA to our DHA, and this conversion is almost non-existent in humans. So it can range to about 0.1 to about 6%, depending on the individual and the life stage. Now, if you happen to be a pregnant female, especially in your third trimester, this can go up to about 10%, I believe. And similarly, your conversion, if you're a pregnant female, your linolenic acid to EPA, it can go up to 20% in that third trimester. So females that are gestating or lactating have a higher conversion rate of your EPA and DHA than equivalent male of the same height, weight, age, etc. So as mentioned before, arachidonic acid is conditionally essential for omnivorous animals. And many people think that dogs are obligate carnivores, but they are not. So dogs, because they are omnivorous, they can actually synthesize arachidonic acid in quantities to meet the needs. If they do not have adequate amounts of linoleic acid, then it will be essential, but they typically get adequate amounts of linoleic acid. Cats, regardless of how much linoleic acid they have, they cannot synthesize arachidonic acid or EPA or DHA for that matter. Therefore, it is essential for the cats and all obligate carnivores. So where do we get these various sources of, what are the sources of these essential fatty acids? Well, it's mainly going to be in plants, nuts, and fish oils. So our fish oils are typically going to be our exclusive source of EPA and DHA. So here we have two common fish oils that you can find. We have our cod liver oil. You can see your EPA 6.9, DHA 11%, alpha, ALA is alpha-linolenic acid, so that's 0.9, no omega-6. Our Menhaden oil, pretty similar, more EPA than DHA, low levels of alpha-linolenic acid, 0 omega-6. Now, you do not have to tell me, regurgitate these numbers at all, but this is just more or less to show you where the essential oils are, or fatty acids are coming from. So our fish has very little omega-6, and I would say this is going to be in wild fish. So if you have our farm raised is going to have more omega-6, unless those fish are provided with more EPA and DHA as their oils when their diet is consumed. So our farm raised is going to have some omega-6 in it. Compare this to our various nuts and seeds. You can see our flaxseed and our walnuts, which are two common foods that they tell you to consume to increase your omega-3s. Our flaxseed, 18%. Our walnuts, 9% of alpha-linolenic acid. You could see here they still have omega-6 in them. And then we have our plant oils. So our plant oils have significantly higher amounts of our omega-6. Canola oil and our traditional soybean oil that we're using, especially in livestock feed, has a lot of linoleic acid as opposed to linolenic acid. In addition, we also can get our EPA from algae. So this is the originator of the EPA and DHA found in fish anyways. In addition, mother's milk. So the DHA has, the infant has a higher requirement while the brain is developing after it's born. So the mother puts a lot of DHA into her milk to meet the need of the infant, and consequently that means that mothers have a higher requirement for the EPA and alpha-linolenic acid. So why do fish have such high levels of EPA and DHA? Well, that all comes from the phytoplankton. So phytoplankton is a big fancy word for algae. So we have different phytoplanktons, and these are the ones that are actually synthesizing the EPA and DHA, and then we just move up the food chain. So then we have our phytoplankton are consumed by our zooplankton or our krill, and then we have our small fish are consuming the krill, and eventually our larger fish such as salmon, tuna, etc. are consuming those small fish. So that's why our wild salmon, tuna, etc. have greater amounts of EPA and DHA in them. Now, I will say they do have a higher level of the delta-5 desaturase in them, so they are better at converting to their linolenic acid to EPA and DHA than mammals are. But it all is mainly coming from the phytoplankton is the main source of our EPA and DHA. So what happens if we have inadequate fatty acids, of these essential fatty acids in our diet? So here you can see on the right-hand side a picture of a rat, and you can see the dandruff on the rat's tail, so it looks very scaly. So they have scaly, dry skin. They also have an unexpected decreased body weight. They have an enlarged heart, irregular estrous cycles in females, reduced fertility and lactation. They have higher amounts of blood triglycerides and uncoupling of the oxidative phosphorylation. So this is a slide showing the fatty acid composition of many common oils or fats. So here you could see butter versus beef tallow versus palm oil, and you can see that these have a significantly higher amounts of our saturated fats, as indicated by this pink dots, and then they have some monounsaturated and very little of our polyunsaturated, and we don't distinguish too much our omega-6 versus our omega-3. And then we have our next classifications are, so we have olive oil, canola oil, peanut oil versus lard. And here you could see our olive oil has a little bit of saturated fats, a significant amount of our monounsaturated, and small amounts of our omega-6 and omega-3. So it really has a favorable mixture of our monounsaturated omega-6 and omega-3. And it also, because we have this monounsaturated, it's slightly more stable than our regular vegetable oils. Compare that to some of our more commonly used oils, our corn oil, soybean meal, very little saturated, a little bit of monounsaturated, primarily omega-6, a little bit of omega-3. And our flaxseed has the highest concentration of our linolenic acid. Here's a list of the fatty acids commonly found in tissues. So we have our myristic acid, which is found attached to the N-terminus of the plasma membrane-associated cytoplasmic proteins. Our palmitic acid here, this is the most common end product of fatty acid synthesis. So as soon as we get 16 carbons on our chain, we stop. So the majority of our fats that we are making is palmitic acid. And then we have our essential ones, linoleic, linolenic, and arachidonic. Now, if you're looking at our diets that we're eating, now all monogastric animals are basically you are what you eat in relation to the amounts of and types of fats. So we don't have any bacterial fermentation beforehand, so whatever reaches our small intestine is what we're going to be absorbing. And what we absorb is what we're going to be putting into our cell membranes. So we are what we eat. And we have the ideal ratio of our omega-6 and omega-3. And if you look at this ratio, Americans have a functional deficiency in omega-3 fatty acids. Last century, in the early 1900s, the ratio was 6:1. So for every 6 grams of omega-6, we had 1 gram of omega-3. Currently, so as of year 2000, our ratio is 20:1. So we now consume 20 grams of omega-6 to 1 gram of omega-3. And this is due to we eat limited amounts of fish within our diets. And this is basically, we have a deficiency in our omega-3s, so we have reduced amounts of EPA and DHA. So if you remember those conversion rates, going from linolenic acid to EPA is 1 to 3%, and it ranges between 0.2 and 8%, and this 8% is more dependent on the individual and the physiological stage that individual is in. Going from EPA to DHA, we have less than 1% average, and this ranges from 0.13 to 6%. Again, depends on the physiological stage of that individual. So really, the only practical way to increase the amount of EPA and DHA is to increase the consumption of fish oils. Now, if you are vegetarian or vegan, you could also take supplements, algae supplements, because some companies actually isolate the EPA and DHA from the algae or the phytoplankton, and so you could take those if you are vegetarian or vegan and don't want to consume fish oil. The next fatty acid that we're going to talk about is conjugated linoleic acid, or CLA. You may have heard about this. There was a lot of research evaluating and investigating CLA in the late 1990s, early 2000s. And basically, CLA is a collection of isomers of octadecanoic acid. And basically, we have both a cis, the most common one is cis-9-trans-11. So it's 18 carbons long with 2 double bonds. So here we have linoleic acid compared to cis-9-trans-11 CLA. So here, starting at the methyl end, counting, we can see we have our this may be backwards, so this should be, oh no, sorry, this is counting from the delta end. So our cis-9-trans-11 counting from the delta end. So starting with that is number 1. So this is number 9 and then 11. The main difference is that we do not have a methylene group in between. So you can see here, this is our methylene group. And in our linoleic acid, we do not have that same methylene group on our CLA. Our CLA was first discovered when they were trying to prove that eating a lot of red meat and animal products is carcinogenic. And they actually isolated many found within ruminants that are carcinogenic, these different isomers. However, they found that CLA was actually cancer prevention. It had some preventative qualities to it. So it's found in ruminants, and this is because, if you remember, our ruminants do not like our unsaturated fats. Those are very toxic to them, so they convert our unsaturated fats to saturated fats, and sometimes they are not adequately efficient at it, and so then we get the formation. Ruminant products have higher amounts of CLA, and this is mainly coming from this butyrofibrosylvan microbe found within the rumen that synthesizes the CLA. You can also get this by the desaturation of vicinic acid. And as I said, it is a cancer prevention. It has antioxidant properties, and it also decreases the growth of the cells. So if you have tumor cells, cancer cells, it actually inhibits the growth. It stops all the signaling molecules for it to keep going through cell proliferation. Okay, next we're going to talk about some of our complex lipids. So the first category is going to be our triglycerides or triacylglycerides. As I mentioned, these are abbreviated as TAG. So our triglycerides have a glycerol backbone. So here is a picture of our glycerol. We have 1, 2, 3 carbons, and our glycerol molecule has 3 hydroxyl groups. And this is a metabolite of our glucose metabolism, and it is the backbone of our triglycerides. So sorry, I'll do that again. Backbone of our triglycerides. So we form our triglycerides by esterifying our fatty acids to the glycerol molecule. So here we have our glycerol and our fatty acids, and you can see we're using the carboxyl terminal end that is binding to the hydroxyl group. So therefore, we end up getting 3 waters synthesized. So this is a dehydration reaction. So this is an example of dehydration. 3 waters are removed, 1 water for each esterification or ester bond that is formed. So here we have our ester bond, which is our carbon, oxygen, carbon, double bonded to an oxygen. So this is our ester bond right there. Our next category of our complex lipids is our phospholipids. And phospholipids are very critical because this is what is making up our cell membrane. And other organelle membranes. So here you can see we still have this glycerol backbone right here in this dark brown. And then we have 1, 2 fatty acids conjugated to it. So you can see our ester bonds. And then we have the thing that's making it a phospholipid is we have a phosphorus-containing group. And this is what's making the phospholipid have a polar end. So we have a glycerol backbone, 2 fatty acids, and our phosphate-containing group. And these most commonly are choline. So if choline is conjugated, so if this is phosphatidylcholine, that's also referred to as lecithin. If we have serine on there, it's phosphatidylserine. And then if we have ethanolamine, it's ethylene. Now, interesting, phosphatidylserine specifically, these ones are going to be facing the cytosol. Unless the cell has been signaled for apoptosis. And once we have apoptosis signaled, this flips to the outside, and that's one way that you can actually analyze and evaluate the stage of apoptosis within a cell. If there's a lot of phosphatidylserine on the surface of it, then it is undergoing apoptosis. Next, we're going to talk about our derived lipids, focusing first on cholesterol. Cholesterol is probably one of the most misunderstood and wronged lipid compound. So it really has a bad rap, but it's very critical. It's a very important metabolite. One, it is needed for proper steroid hormone synthesis. So we need it to make our sex hormones. We need it to make our stress hormones, our corticosteroids. We also need it if we're going to rely on the sun to make our vitamin D. It's a precursor for vitamin D. We need it for adequate bile salt formation. And it also is a major component of the cell membrane. So plants and bacteria do not utilize cholesterol where we do. And by utilizing cholesterol, that's what's helped us not need a cell wall. So it maintains the structural integrity and the fluidity of the cell. So that's why we don't need a cell wall. And a lot of people think that cholesterol is high in fats, and that is incorrect. It actually has the highest concentration in muscle because we have the most amount of cell membrane that we need to maintain. So our muscle actually has the highest concentration of cholesterol in it. So how do we synthesize cholesterol? Well, we need to utilize acetyl-CoA and acetoacetyl-CoA, and these converge to make HMG-CoA, and then we end up using HMG-CoA reductase to start the conversion to malvinolate, and eventually it ends up making cholesterol. But the HMG-CoA reductase, this step is the rate-limiting step. So because this is the rate-limiting step, this is where we have developed many use of the statins. So the various Lipitors, et cetera, that are limiting cholesterol synthesis. If you have high cholesterol, your doctor may prescribe Lipitor towards you, and Lipitor is a statin, and it's inhibiting your HMG-CoA reductase. However, that doesn't just affect cholesterol, so you can see all of these other reactions that it is limiting. So therefore, we also inhibit the enzyme ubiquinone, or the enzyme that's making ubiquinone, or CoQ10. And if you're ever up super early on a Sunday morning listening to the radio, many times you'll hear many infomercials, one of which is convincing you to take supplemental CoQ10. I think a lot of bodybuilders and elite athletes increase the amount of CoQ10, and that's because this is part of the electron transport chain. So this is one of the proteins that is actually transporting the electrons. So it is thought that if you have more CoQ10, you'll increase the amount of ATP that your mitochondria are making. So if you happen to be taking a statin or know someone that is taking a statin, such as Lipitor, those individuals probably need to supplement with CoQ10 because by decreasing cholesterol, they are also inadvertently decreasing the amount of CoQ10 they are synthesizing. So as I mentioned, cholesterol is a precursor for many hormones. Here's a whole list of them. You by no means do not need to know these, but you can see all the hormones that you are affecting. If you are taking these various statins, you're going to be decreasing the amount of your sex hormones and your stress hormones. Cholesterol, as I mentioned before, is also a precursor for vitamin D. So we have our cholesterol is converted to dehydrocholesterol, and this is what's put on the surface of your skin. When dehydrocholesterol is hit by UVB light, it is converted to cholecalciferol, and that is our vitamin D3. So if you are taking statins or if you are trying to reduce the amount of cholesterol that your body is making, you may inadvertently be affecting the amount of vitamin D that you are synthesizing, which if you're not taking supplemental vitamin D with your statins and you're older, which usually you're less efficient at making vitamin D, you're going to be more prone for osteoporosis. And osteoporosis can affect both men and women. Okay, the next group of derived lipids are eicosanoids, which are our prostaglandins. Sorry for my poor writing, and our leukotrienes. So what are eicosanoids? They are compounds derived from 20 carbon and 22 carbon fatty acids. So we're getting them mainly from arachidonic acid, EPA, and DHA. And they synthesize prostaglandins, prostacyclines, thromboxanes, and leukotrienes. And these have a hormone-like role in vasoconstriction and blood platelet aggregation. So here I'm going to take you through the pro-inflammatory. So this by no means is going to be on the exam. The only thing that you really have to know is that the omega-6 are pro-inflammatory, omega-3 are anti-inflammatory, but for those of you that are interested as to why, here's a nice little picture. So here we have a stimulus that's going to end up, we have higher amounts of calcium. That's going to cause the breakdown of our arachidonic acid. AA is arachidonic acid. You don't have to know these enzymes. And we get the formation of LTA4. That's then converted to LTB4. And that then is a chemoattractant, or a chemokine or a chemoattractant, which is going to attract our leukocytes, which is our white blood cells. Which includes granulocytes, macrophages, and T cells. And so all of these are going to come to that location. At the same time, we're going to have our LTE4 that's formed, and this is going to cause bronchoconstriction and vascular permeability. So we need these immune cells to be able to come to the location, so we increase our vascular permeability. So that's how our pro-inflammatory fatty acids or omega-6 fatty acids, why they're pro-inflammatory and how they're signaled. So how do the anti-inflammatory eicosanoids work? Well, basically, you can see, as I mentioned before, our EPA and our DHA, you can see here that they are using the same enzymes as our arachidonic acid. So here, our arachidonic acid is broken down. We get free arachidonic acid with compromise in our membrane. We're going to have our free arachidonic acid is going to have inflammatory effects here and here. However, if we add EPA and DHA, if we have a higher concentration, they're competing for the same enzyme. So we have COX-2 and LOX-5. And so these, if we are breaking down EPA, we're going to have more anti-inflammatory effects, and it's inhibiting the breakdown of the arachidonic acid. And it also, our EPA is inhibiting our NF-kappa B, which is also making our pro-inflammatory cytokines. So that's another way that it's reducing. That hopefully clears up. You by no means have to know this specifically for the exam. Just know that our omega-3s are anti-inflammatory.